Okay, we will be going over our Unit 1 review. Okay, for our first problem, we have a limit problem, and we need to first substitute in. And notice when we do substitute in, we should end up with 0 over 0. So I need to factor or do some kind of rationalizing, but with this problem, it is a factoring problem. And we're going to have x cubed plus 4. In the denominator, we have x squared is common. So we're going to have 5x squared plus 6 left. Our x squareds are going to cancel, and so now we're ready to come back and look at our limit as x approaches 0 of 3 times x cubed plus 4 over 5x squared plus 6. And when we reevaluate our limit now, we're going to have 3 times 4 over 6, which is going to be 2. And that is going to give us answer choice C. All right, moving on to our next limit. Now we are approaching 3 from the left. Now we still need to substitute in, though, just to see what we're going to get. And if we do our substitution in the numerator, we're going to have 4 minus 9. In the denominator, 3 minus 3. So notice we have negative 5 over 0. Now it's tempting to write does not exist. However, this is one-sided, so we can't write does not exist. We need to go and investigate a little more. And this is where we went through and we needed to pick a value super close to 3 but to the left. So we're going to choose something like 2.99. And when we sub in, we're really looking more or less at the sign. We're not so interested in number crunching. However, we can, but this is non-calculator, so it would be a little much. And notice in the numerator, I get a negative value. And then in the denominator, I'm going to get a negative value, which is going to give me a positive. So this should be tending toward positive infinity. It looks like at x equals 3, we have a vertical asymptote here. Okay, for our next problem, it looks like it is talking about their intermediate value theorem. Notice we are told that the function is continuous on a closed interval from 3 to 5. So this is setting up our information we need for the intermediate value theorem. We are also told that f at 3 is 9, so I have an ordered pair 3, 9. And then I also have another ordered pair, 5, 22. So I'm over here at 5, way up here at 22. And so here we're asked, well, which of the following is guaranteed by the intermediate value theorem? And we have to be careful here about looking at what's guaranteed. Remember that it's saying that if we have some k value inside this interval, then there has to exist some c value down here so that f at c equals k. Now, the only two that are dealing with some y values that make any sense in this problem would be either a or b, but only one of these can be true. Now, looking at part B, I want to choose that, but 4 is a very specific value. We were just told that there is some c value so that f at c is equal to k. I don't know that c value for sure, so this is too specific for us to use. Now, A should be the correct answer. Notice how they did not try to pinpoint an x value. They're just saying, okay, that x value is there. 11 has to be between 9 and 22, and it is. So A should be our correct answer. All right, number 4, this is getting our definition of a derivative. We're getting closer. So what we need to do with this one is evaluate each individual part. So in other words, we're going to look at f of x plus h, and that means where I see an x, I'm going to put x plus h. So this is going to be 3 times x plus h, all squared, plus 4 times x plus h. And then we're going to go through and FOIL this out. So I'm going to have 3 times x squared plus 2xh plus h squared. And then I'm going to go ahead and distribute over here. And so finally, I have 3x squared plus 6xh plus 3h squared plus 4x plus 4h. Now that's taking care of this little portion here. So let's come back and put all of that together and look at our limit. And so we have the limit as h approaches 0. And I skipped this part, but I should have substituted in 0 for h. And if I did, here I would have gotten f at x minus f at x over 0, which does lead to 0 over 0. That's why I went through this other part. All right, so coming down here, f of x plus h is equal to this terrible mess that I have here, 3x squared plus 6xh plus 3h squared plus 4x plus 4h. And then we're going to come back and notice the rest of this says minus. So I'm going to do a minus, and then f of x, which is all of this. So I'm going to put that in parentheses to make sure I do subtract each term. And then coming back, all of this is over h. All right, so I sure hope we can simplify something here. So looking through this, it looks like we should be able to cancel out this 3x squared and this one because we are subtracting and distributing that negative. So that means we also have a 4x we can cancel. All right, so now I have the limit as h approaches 0 of 6xh plus 3h squared plus 4h all over h. And if I reapply my limit again, I do get 0 over 0. I do have a GCF though, so I'm going to factor that numerator. So again, I'm just going to carry all of this through. And if I factor out an h in the numerator, I have 6x plus 3h plus 4. That's all over h. And so now I see that those h's are going to cancel. And now when I evaluate my limit, that term is going to go to 0. So my answer here should be 6x plus 4. So that's answer choice B. All right, for number 5, we need to answer which of the following is the reason why our function is not continuous at x equals 2. So the first thing we need to look at is g at 2 defined. That was our first step with all of these. And notice g at 2 is defined right here. That's where x is 2. And if we sub that in, we get 2 root 2. So we know that g at 2 is defined, so that's going to eliminate answer choice 1. So now let's go to the second one. Let's look at our limit. And we do need to remember that the limit as x approaches 2 from the left has to be equal to the limit as x approaches 2 from the right. And so let's go see where we're going to get. Right up here, we're going to have sine of 2 pi over 3. And sine of 2 pi over 3, that's going to be positive root 3 over 2. And now from the left, this is what we're looking to see if this is going to be true. From the right side now, that's all these values bigger. So I'm going to plug in and I'm going to have 2 root 3 over 2. And so that looks like that's going to reduce down to root 3. So those are not equal. So the limit does not exist. That is true. And then now let's look at 3. The limit as x approaches 2 g of x doesn't equal g at 2. That is true because g at 2 is defined, but the limit does not exist. So that is also true. So that means we have answer choice D. Right, now we're going to talk about that power struggle because now x is approaching infinity or negative infinity. And so anytime you have that, do remember this is talking about your horizontal asymptotes. And so we need to isolate the highest power on top. And then we also need to isolate the highest power on bottom. And notice for these that we are balanced. So that's good. So those powers would cancel each other out. And so my limit here is going to be 8/3. So we have answer choice C. Over here on number 7, we are approaching negative infinity, but it's still looking at your power struggle. So I have a negative 3x. However, on bottom, that is the square root of x squared. Now, we have to be careful. Don't assume that that is just x. We don't know if that x value is positive or negative, so we need to keep it absolute value. So now we need to talk about this negative infinity. I'm going to give negative infinity a code name. It's going to be called negative big. So I'm going to see what happens if I plug in a negative big number. And so let's see. On the top, I'm going to have a positive big. And then notice in the bottom, I've got, let's see, 3 times a positive big on top, over a positive big on bottom. I didn't bring over my 3. And notice now that tells me those are going to be balanced. So it looks like my value is going to be positive 3. Okay, number 8, which of the following statements would be true? So again, going through, looking at the first statement, the limit as x approaches 2 from the left. So from the left would be this portion here. So I'm going to plug in up there, and I'm going to have 2 squared minus 3 times 2. So that's going to give me negative 2. So that tells me that that is definitely true. And notice this 2 only, you know that's going to be gone, and you know that's going to be gone. So notice that really the only other one I need to test is option 2, and that's saying that this limit exists. Well, I know the limit from the left is negative 2. So now let's look at our limit from the right of h at x. And so if I go back and plug in here, I'm going to get 4 minus 5. So I'm going to get negative 1. So that limit is not going to exist. There's no way you can be continuous. So this is going to be answer choice A. Okay, for these true false, this is just some good practice with our limits. And I would think of this as 2 different problems. And you're just trying to see, are you going to get one side to look like the other? Now, on number 9, this portion here, we need to put those 2 together first. So that's going to be a common denominator. So I can go ahead and look at the limit as x approaches 4. And that's going to be 2x minus 8 all over x minus 4. And then with this, if I plug in, I am going to get 0 over 0. So I need to go through and see if I can't factor. And it looks like I'll be able to factor out a 2. And that's going to leave me with x minus 4. So those are going to cancel. So that limit is going to be 2. So I know the left side here is got to be 2. Now over here on the right side though, notice how it wants us to evaluate this limit here first. And if we do that, notice I'm going to get 8 over 0, which is going to be a does not exist because it's not a one-sided limit. So for number 9, that is going to be false. Okay, now looking over at the next problem, number 10. If I plug in 1, I will get 0 over 0. So I definitely need to do some factoring here. And in the bottom, same thing. And notice those minus 1s will cancel. And now when I go back and evaluate that limit, it is going to be 8 over 7. Over here, if I look at this separately, then if I substitute in a 1, I am going to get 0 for this top limit and then 0 in the bottom limit, but notice they are separated from each other. So here, this is going to end up being false because the way this is written, it is not lending itself to this rational fraction that can be reduced. Okay, looking at number 11, with this one, then again, we're going to sub in a 1 on one side. And if we do, we have negative 2 over 3 minus 4, negative 1. Over here on the right side, I'm going to plug in, and I'm going to have a negative 2 over, and if I plug in 1, I'm going to get negative 1. And now this time, notice what happens. There's nothing here for us to factor, so this one ends up being true. So that does change things a little bit there for us. Number 12, we have this limit of x approaches 5 of f of x is 2, and then this limit here is 0. Then the ratio of that limit does not exist, and that one is true. We can look at that ratio from that point of view, from that direction. All right, so now let's look at 13. Now 13 is trying to trick us because 12 was true. Kind of makes us want to say 13 is true, but it's not. That is false. If I get 0 over 0 here, notice in that situation we had to factor and cancel. We probably had some kind of removable discontinuity. All right, number 14. If this limit exists, then the limit must be that. That is going to be a false. You don't know if that is continuous. You're not told that, so nothing says that has to be true. However, number 15 must be true because p is a polynomial and polynomials are always continuous. So that is something that would absolutely have to be true. Okay, looking at number 16, here we have infinity and then minus infinity. That is never ever going to be true. That is an idea of a big number, and this is an idea of another big number, but we don't know if those big numbers are the same. They're just big numbers. All right, number 17. If the line x equals 1 is vertical asymptote of this function, then f is not defined at 1. That would be false. If we look at a vertical asymptote here, and so let's say we have this vertical asymptote. Now, who's to say that I don't have just a random point thrown in right here? For the function itself, might could run this way and this way, but I might have just a random point sitting there. So we have to be careful with that. That is going to be false. All right, number 18. F is bigger than 0 and f at 3 is less than 0. And that kind of is making us want to say that the intermediate value theorem, because we did talk about a positive and a negative. But here's the thing, we don't know that f is continuous. So this one is false, and it's kind of misleading because it didn't say f is continuous. Notice number 19, it starts out with f is continuous. So that's a little bit different here. So we do have to be careful and watch for that. Number 19, f is continuous at 5. F at 5 is 2. F at 4 is 3. So then this limit is 2. So, well, I don't know. Let's go plug in and see. So if I sub in there, then I've got 4 times 4, 16. So this is going to be the limit as x approaches 2 of f at 5. And so let's see, then that's going to turn into, here it's really not mattering what that is approaching. So it looks like this is going to end up being 2 here. So number 19 is true. Number 20, this graph we've seen quite a bit. This is false. Do keep in mind this graph. We have the open circle and everything approaching positive infinity is running with 1. negative infinity, negative 1. And that graph is so important for us to learn. Notice that we don't have any defined values there at 0. Number 21, be careful with this. Again, it's wanting us to assume that our function is continuous. We've not been told that, so this would be false. Number 22, if f is undefined at x equals c, then the limit as f of x as x approaches c does not exist. Well, no, that's going to be false also. Think about if we just had a nice little line here with an open circle in it, then we have a function undefined at x equals c here, but does that limit still exist? It sure does. So 22 is false. Okay, with 23, with sketching here, and you could come up with a couple of different sketches for this. I'm going to go through and grab some for sure things that we need to make sure we have. One of them is going to be f at 0 is negative 1. So that means I should have a point right here at 0, negative 1. Now, a couple of other things that are making me think, hey, I need a vertical asymptote here. That's going to be these two right here, here and here. Notice as I'm approaching 2 from the left and right, I've got some infinity business going on. So that means definitely I'm going to have a vertical asymptote through here. Something's going on with that for sure. Okay, and let's see, what else do we know? The limit as x approaches 0 from the right is negative 2 and from the left is 1. I'm going to hold off about that one for a minute. And let's see if we've got any more asymptotes here. Right here is an end behavior. As x approaches infinity, our function is approaching 3. So I know that means now I can cross a horizontal asymptote here in the middle of the graph. It's just talking about our end behaviors. And it also looks like here at 4. So looks like we've got a couple of asymptotes here going on. Kind of strange looking for sure. And now let's talk about what's going on at 0, because I've got just about everything else I can on this graph. Notice that the limit as x approaches 0 from the right is negative 2. So I'm going to go to 0, negative 2, and I'm going to put an open circle because I already have a defined value there, and I've got to keep this as a function. And so I know from that side I'm approaching positive infinity. So it looks like you might be doing something like that. And then let's see, that took care of that one. And this other one, x approaches 0, I'm going to be at positive 1. So I'm going to do an open circle here at positive 1. And notice that one's telling me that as I'm approaching there, I've got a 1 going on. So, all right. And as I go toward negative infinity, I'm flattening out at 4. So I think this one's probably going to do something like this. And we've still got one more side though. We have this other side where we're tending out toward infinity. And notice it says as we approach infinity, where'd that booger go? We're approaching 3, so I know this has to run something like this through here. And you can change this up a little bit, but do make sure you understand the idea of the asymptotes here and how a limit can exist at an open circle. Okay, for this next problem, we're going to have to use both a function and the graph to help us through this one. So for the first part, notice we are approaching 2 from the right. For f of x, so 2 from the right is going to come in this side and looks like we're going to be at positive 1 plus 5 times, and for g of x, we're going to go up here. That's going to be the square root of 4 plus 4, 8. And so whether or not you leave it like that or you rationalize it, it just depends on what your answer choice is going to look like in a multiple choice setting. Remember, that can be rewritten as 2 root 2, so you might see this written as 1 plus 10 root 2. As far as what I'd rather you write, I don't care. Whichever one that you want to is fine. Part B, again, we are subbing in here at 1. So f at 1. So over here, we're going to be approaching 1. And it looks like we're going to be down here at negative 2. And then times, and if I evaluate g at x, up here at 1, that looks like it's going to be times the square root of 5. All right, part C, the limit as x approaches 2 from the left of f of x. From the left is going to be negative 1 over, and then the denominator here, if I plug in 2, again, I'm going to get the square root of 8. And you can leave it like that, or you could see this 1 over 2 root 2, which is probably what you'll see it. And ever so often, you might see this as root 2 over 4. But more times than not, you'll probably see it like this. All right, so for part D, that square, you can move that out and think about this as the limit as x approaches 4 of g of x, and then all of that squared if you want. You certainly can do that. The limit as x approaches 4 of g of x, well, that's going to be the square root of 4 plus 16, so 20. And then all of that squared is just going to give us 20. Okay, for our next problem, you are asked to solve this for k and m so that we are continuous everywhere. And so whenever we do that, this is where we looked at our limit as x approaches, and for this case, negative 2 from the left of f of x equals the limit as x approaches negative 2 from the right. And so what you're going to do is sub in negative 2 in place of x, and then also down here sub in that negative 2 and set these equal to each other. So you're going to have negative 2 all squared minus k times negative 2 plus 3, and you're forcing this to be equal to 2 times negative 2 minus 3. So we're going to have 4 plus 3, 7 plus 2k is equal to negative 7. So to solve this here, notice we'll subtract negative 7 over, divide by 2, so k is going to be negative 7. Now to find m, you're going to have to do the same thing, same process, but with different equations. So now we're going to look at our limit as x approaches 3 from the right or left, it's not going to matter, of f of x equals, and then the other side. And again, we're substituting in. So when we plug in here, we are plugging in 3 in place of x. So that's going to be 2 times 3 minus 3. And then on the right side, that's going to be 4 minus 2m. So here 4 minus 2m equals 6 minus 3, or 3. So negative 2m equals negative 1, so m is 1/2. So you have found your values for k and m so that this function is continuous everywhere. All right, so for our next problems, we're going through and just evaluating here. And so we have our absolute value function, and sometimes it helps to see a graph of those. Do remember the absolute value function looks something like that. And so it's a nice little function. If we plug in 0 here, then we are going to get 0. Now if we plug in, let's say negative infinity, keep in mind negative infinity as your function is tending this way. Our function is, or has our x values tend toward negative infinity, our function values tend toward positive infinity. the absolute value of x over x, again, that function comes up all the time. It's a good idea just to commit this to memory just like you would any other parent function. And so we see that that limit as x approaches 0 does not exist. The limit as x approaches -5 is going to be -1. These is that 1 and -1. I forget to label that. And even as x approaches infinity, notice that this is at 1. This, if you picture this as a graph, that's just a horizontal line at 6. So there's your graph here at y equals 6. And so notice no matter what your x value is approaching, your y's are stuck at 6. Cosine, that graph here, remember it starts way up there at 1. And this is a periodical function. It does repeat itself over and over and over. And so as x approaches 0, remember cosine's up here at +1. Now as x approaches infinity, as my x values grow without bound, notice that the y values are actually bounded. They are oscillating between +1 and -1, and they're not approaching a specific value. So we're going to say does not exist. Okay, our graph for 1 over x, good idea to notice that one, and remember that that graph does have an asymptote here at 0 and has a vertical asymptote also here on the x-axis and runs something like this. And so now we can see as x approaches 0, that definitely does not exist. And then as x approaches positive infinity, then we are approaching 0, and over on negative infinity, we're also approaching 0. For our rational function, we can plug in our 1 here, and so you're going to end up with 5 over -1, or -5. As x approaches 2, notice you're going to get 6 over 0. This is not one-sided, so you can write does not exist. That means we do have a vertical asymptote. As x approaches infinity, then that's your power struggle, and these powers are balanced, so that is going to tend toward 1 and also toward 1 down here. All right, so for part G, again, same kind of idea here. Now notice if we plug in 0, then we're going to get, let's see, 0, we're going to get -2 over -4, so that is going to lend to 1/2. If we plug in -2, though, notice we're going to get a -4 over 0. And again, this is not one-sided, so we're going to say does not exist. If we plug in +2, now this is going to be a pain in the butt because you get 0 over 0. So we've got to come back over here, and we're going to have to do some factoring. And notice that does cancel, so we have 1 over x plus 2. And if we plug in here, we have 1/4 as our limit. Now, again, this would have been a removable discontinuity. Just food for thought here, it's removable. And that removable point is at 2, 1/4. All right, and then our power struggle as x approaches positive infinity. We have more power in the denominator, so this is going to go towards 0 in both cases. Okay, and now part H, we're going to look at that reciprocal. And so again, we're going to substitute in 2, and if we substitute in 2, we are going to get 0 over 0. And again, that means we have some kind of removable discontinuity here. We're going to have to factor and do some canceling. And so now when we reapply that limit, we are going to get 4. As x approaches 0, we get +2. And as we tend toward positive infinity, then it looks like this is going to be positive infinity as well. negative infinity, negative infinity. Now, if you're not sure, look at what was left over here. You remove that. So f of x actually reduced down to be x plus 2 with a hole in it at set x minus 2 equal to 0. So the hole is at 2, and then the y coordinate is going to be at 4. So you have a removable at 2, 4. And so when you graph this, you're going to have something that looks like this. With that 2, 4 missing, you're going to have a 0 in there. So let's go back and remove it. 2, 4 maybe. We're going to have an open circle. And so it helps us see, too, that in behavior, as x is approaching negative infinity, the y values are approaching negative infinity as well.